When working with a current divider, it's a very handy rule to understand, and we'll be using this a lot in all future lessons where we've got division in a series parallel circuit. That is, we've got a current travelling along which then forks or splits or divides, if you like, into more than one branch current. While you can use simple Ohm's law to derive the individual branch currents, sometimes, especially if you haven't got the voltage across that network, it's ideal if you do have the equivalent resistance and you've got the total current flowing into the node. You can work out individual branch currents with a very simple equation. And the current divider rule I've sketched up on the board, Req of the entire network divided by the resistor that you want to find the current going through, Rx, times I total, and I might just put there I node, because it's really the current which is coming into the node. And of course, I know the camera, the way it's set up, you can't see everything on the bottom of the screen, but it says the current leaving a node must add to the current entering the node. So where I've got another node down here and I've got current leaving that node, the current which comes into that network has to equal a current going out of the network. So that is to say that the algebraic sum of the individual branch currents has to add up to, in this case, the total circuit current. To work out the Req then of this network, I've used product over sum, simply R1 times R2 divided by R1 plus R2, to come up with 85.7 ohms based on 300 ohms and 120 ohms of resistance in this network. And then I've applied the current divider rule to work out the current in the first resistor, IR1. So Req divided by the value of R1, 300 ohms, times the total current in the circuit in this case, because knowing that we've got an equivalent resistance of 85.7 allowed me in this very simple circuit to work out the total current flowing in the circuit, which is 1.86 amps. So that 1.86 amps flows into the first node and then it forks into two branch currents. So that's why I have to use it here. It's the I node or I total in this particular circuit. 531 milliamps is flowing through the 300 ohm resistor, and note that is a lot smaller than the 1.33 amperes of current flowing in its buddy over here, which is only 120 ohms. Lower value of resistance, much higher current flowing through that lower value of resistance, and hence IR2, Req divided by the value of R2 times the node current to give 1.33 amperes. And to run a quick test on that, if we add the 531 milliamps to the 1.33 amperes of current, we'll come back up with our 1.86 amperes of current flowing into the node. So we learn this in about week 3 or week 4 of the DC circuits syllabus. And we'll be using this every week from now, especially starting in this week using series parallel. We'll be working with some circuits that have multiple current paths. Now I do have one other thing set up on the board which I'll just slide across. So in this circuit I have a supply voltage and I have 4 individual resistances. I have a circuit current flowing from supply 942 milliamps, and each resistor value is written here on the circuit, and we're tasked to find out what the individual branch currents are. First thing that we have to do is work out the total resistance. In this case, we'd have to use the reciprocal rule, or the sum of the conductances, so to say, and we come up with 127.4 ohms of total resistance, and then multiplying the total circuit current times that resistance, we come up with the fact that we've got 120 volts of supply voltage coming into this circuit. We can work out the total power in the circuit by simply the supply voltage times the circuit current. We've got 113 watts, and then that's the total power. The individual resistance powers, we'd be able to work out a variety of ways. We could use I squared times R, we could use V squared on R, or we could simply use the individual voltages times the individual branch currents. That takes us back to the branch currents again. To work out the branch currents, then, using the current divider equation that we just saw, Req on Rx times I node, I've applied it here for I1, I2, I3, and squeezed onto the side of the board over here, I4. And again, using some common sense and saying the smallest value of resistor must have the largest current going through it. 330 ohms is the smallest resistance, I4, and we look at I4, find out that we've got 364 milliamps of current. And that 364 compares with 176, 146 and 255 milliamps. So of course the 820 ohms is the largest value resistor here. So that must have the smallest amount of current going through it. The smallest branch current, I2, we check that, I2, 146 milliamps. It is in fact the smallest current. So again, the current divider rule, something which we'll be using every week for solving branch currents in more complex circuits. This has been Greg Moore for TAFE New South Wales with a small overview of current dividers.